All right, let's take a look at what we've got for our bell work here. I would say that this is, while certainly probably like the upper level of what you could expect to see, certainly within the reasonable bounds of what you could expect to see on, say, hypothetically, tomorrow's quiz that you guys have. So in this case, we are given that we're given that we are looking at a binomial experiment, some kind of binomial distribution, where we are told that the probability for success, or P, of a particular trial is equal to 0.72, and that we are running 7 trials. Okay. And we want to know what is, first of all, the probability that we see 5 or more, or another way to say that, at least 5 successes out of those 7 trials. Okay. Awesome. So what do I do here? What's the game plan? Say again. That is not quite going to get me where I need to be. So first and foremost, what is the at least 5, or what does the 5 or more translate to for our purposes? 5, 6, or 7. So this is the probability that either x is equal to 5, that we see 5 successes, or that we see 6 successes, or that we see 7 successes. Okay. What should I do with each of those probabilities if it's a bunch of OR statements? We're going to add them together. Do I have to worry about overlap here? No, I can't get both exactly 5 successes and also exactly 6 successes. That's not going to happen. And so these are just all mutually exclusive. We can just do the probability of getting 5 plus the probability of getting 6 plus the probability of getting 7. Okay. So what is our formula for figuring out, we'll just go one at a time here. What's the formula for figuring out the probability of getting 5 successes here? So this is going to be 7 choose 5, which is the number of ways that I can get 5 out of 7 successes. Okay, and then what am I multiplying by? 0. So number, or the likelihood of a success, and then how many successes do we have? To the power of 5. Times 0.82 to the power of 2, because we fail twice, and there's a 28% chance of failure. Plus 7 choose 6, exact same setup, but we are now raising to the power of 6 and then to the power of 1. And then 7 choose 7. 0.72 to the 7 times 0.28 to the power of 0. Yeah. Mm-hmm. Someone want to help me out? Why do we have to put the 7 choose 5? What does that do? So we have 7 trials and we have 5 successes. And so why do we do 7 choose 5? What does the 7 choose 5 tell us that we're allowed to do? So they have this correspondence of that's the number of successes, that's the number of total trials. But why do we have to multiply by this at all? What does this do for us? Does the order in which we get a success or a failure matter? No. We can get successes and failures in any order we want, right? This could be success, 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 fail, fail. But it could also be fail, success, success, fail, success, 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 success. And it could be any other way that I can arrange it. This is the number of ways that I can arrange it. 7 choose 5, right? I have 7 slots. 5 of them are going to be successes. 2 of them are going to be failures. So 7 factorial ways to arrange 7 objects, dividing out the 5 factorial successes that are going to be the same, dividing out the 2 factorial failures that are going to be the same, that are interchangeable. And so we need to multiply by that coefficient because there's more than one way to get 7 successes and 2 failures. And that's exactly the number of ways to get that. Good question. Other questions here?
So you said that we get extend the order doesn't matter.
Well, so order matters. So let's be really clear here. What I mean when I say order doesn't matter is that it does not matter, or rather, I want it to be equivalent if I saw failure, success, failure, success, 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 versus success, 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 failure, failure. I want those to be the same. If I just multiply the probability of failure, probability of success, then that's for that specific string of S, 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 F, F. Versus, I don't want it to just be that specific string. I need it to be choose. It is the exact same reason why we do combinations for the cards, because we don't care about the order in which we see the cards when we're constructing our hand. And since we don't care about the order, we want it to all count as the same. Right? So it's the number of ways to get that result. Or maybe even better, the number of equivalent results. If you'd like, pick a smaller sample space. So pick 4 instead. And mess around with how many ways can I rearrange these letters to get distinct strings. It'll be 6, which is the same as 4 choose 2. So play around with it, see what sample space you get, and then know that it works outwards for larger sample spaces.
Yeah, 4
Right, so there's 6 different ways to arrange this. Yeah. Okay, so adding those together to get what we would get, we could certainly do that in our calculator. We have the little cheaty way to do that, which is going to pull up adds for me, which I love. So if we do binomial PDF, if we're doing 7 trials, the likelihood of success is 0.72, and we want to see 5 successes. Okay, plus we want to do the exact same thing, but with 6. And then we want to do the exact same thing, but with 7. Okay, apparently the likelihood of this happening is 69.2% of the time. Okay, for B, figuring out our mean and standard deviation. When we have our binomial probability distribution function, how do we find mu? Number of trials times the likelihood of success. So in this case, our number of trials is 7. Probability of success is 0.72. Just of 1 trial. And so 7 times that, I get our expected value is about 5. Okay, thank you. And who am I emailing? Tolbert. Yeah. Thank you. Okay. How do I find my variance? Which I didn't ask for, but we do need. Yep, so we take this 5.04, multiply it by, in this case, 0.828. To get that the standard deviation is 1.41. And what do I do to variance to get the standard deviation? Take the square root. I get 1.188. For my sake. Ta-da. Which is a lot nicer than having to find the weighted average and then find the weighted average of the x squareds and then find the difference and blah, 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 blah. But so much, much faster. All right, questions with our belt. Okay, today's lesson was one that I was excited for, and then I learned that you guys aren't given tables of z-scores for the test, and so we just have to do all of this in our calculator, which is not particularly, it's not like easier than what we would be doing otherwise. It's just a different thing, and it's just a lot more uncomfortable to teach. So it's just unpleasant for me. So that'll be entertaining, but brace yourselves. Fun calculator lesson ahead. We're going to be talking about carrying on with our kind of what we're going to be doing here, looking at what is called the normal distribution. We're going to see why the binomial distribution and normal distribution tie into each other later on in Unit 5. But for now, this is, you can think of this as just like the next step in the line of, hey, we've looked at PDFs, then we've looked at binomials, now we're looking at normal distributions. Interesting about the normal distribution. This is going to be the kind of first continuous PDF that we look at. So we define the normal distribution to be a continuous, symmetric, bell-shaped PDF of a random variable, which is drawn exactly as you see here in your notes. Okay, a couple of things that we can talk about for the normal distribution. For instance, one interesting thing is that all three of the measures of center that we spoke about, so mean, median, and mode, all occur at the same place. Are all equal. And as you can pretty clearly see with the bell shape, this is going to be a unimodal distribution, right? Only one mode. This is a continuous distribution function, which means that we are going to have a whole range of x values that we can be anything between technically like negative infinity up to infinity in most cases. We could see any x value in between there. For our purposes, though, that's just like the definition of continuous. We know that it's symmetric, so same amount of data on the left and the right. We could also talk about an interesting fact that you don't really see highlighted well in this picture, but is, I think, kind of cool. The curve never actually touches the x-axis. You can think of events that occur around the center of our PDF as being fairly likely, right? That's where they have the highest probability, is where that height is the greatest. And events, the farther you get out to the side, as being more and more unlikely. The idea here, though, is that, yeah, an event might be really unlikely. Like it might be really unlikely that lightning strikes twice in the same place in the same day, but that doesn't mean that it's impossible. And so there's no point where we say, nope, this event is too improbable, it's too unlikely to happen, we're going to treat it as impossible. Technically speaking, we can go out as many standard deviations as we want. And that is perfectly acceptable. So as a result, curve never touches the x-axis. Now, because this is a PDF, what must be true about the sum of all my probabilities? It's going to have to be 1. So the sum of all my probabilities have to be 1. In this case, because we can't look at one specific x value for a probability, for instance, if we just look at like 5 for our x value, that's not going to give us a probability. We have to instead, we have to do this for all of our continuous functions. We have to look at a range of x values. And the thing that's going to tell us the probability that we fall into that range is the area under the curve. So what we see here is the probabilities not represented by the heights, but instead represented by the area underneath or between particular values. As such, if the area under our curve represents the probabilities, what must be true about that area? Since it's a PDF, area must equal, what do we say? 1, because the area is indicative of the probabilities. So this is a PDF where area tells probability. Except it's not actually equal to, it's going to be greater than or less than or whatever. All right. One more small thing that we have talked about before in Unit 3. Because this is a symmetric distribution, the 68, 95, 99.7 rule is going to work. Now, when I first gave this rule, I was kind of quibbling back and forth between like, oh, if we go out to standard deviations, then really it's more like 96% of the data. I have since learned that the 68, 95, 99.7 rule actually applies to all symmetric distributions. 96 works better for standard for the normal distribution. But to keep things general, to say that this is the rule for all symmetric, this is actually the rule that we use. So this is true for all symmetric distributions, and certainly the normal distribution is a type of symmetric distribution. Okay, and so just to remind us what this rule means, we see 68% of our data when we are within 1 standard deviation, 95% of our data when we are within 2, and 99.7% of our data when we are within 3 standard deviations. As detailed here. Now, this ends up, and we'll explore more why this ends up being like the main distribution that we are going to study. But this ends up being like the fundamental distribution that we want to talk about. And so it becomes helpful to, rather than trying to fit a new PDF to our data, to instead fit our data to a conventional PDF. And the way that we do that is through what is called the standard normal distribution, which is the exact same thing as the normal distribution, except we know that this is a normal distribution. Where the mean is always equal to 0 and the standard deviation is always equal to 1. And what this essentially does is this converts our X values into Z-scores. Okay, what was the formula for our Z-score? How do I find the Z-score here? Yeah, this is X minus mu divided by the standard deviation. You can think of this X minus mu as adjusting the center to 0. And you can think of dividing by the standard deviation of our data as adjusting the standard deviation to 1. And so this takes an X value and turns it into a standardized Z-score, which is just, rather than having to learn or create a new distribution every single time. We just need to adjust our values, which is nice. Nice that we can do this. And then this is just always going to be the convention. Z-scores are going to be given to 2 decimal places, and that's mostly just because of the tables that people used to look at. They only go to 2 decimal places, because otherwise it would be a pain in the butt to look at these for more. So you can think of rounding to 2 decimal places or to the hundredths. Either way is fine. I mean, it's equivalent, right? Those are the same thing. Okay. So ultimately, this is not what we're going to do. I do want to show you an example of what this would look like, mostly because I'm nostalgic and old and not willing to let technology make me obsolete just yet. So we are going to take a look at an example of how I would say this is conventionally done. And then I'm just going to show you how to enter these values into your calculator, and it's going to make it like really easy. Not that what we are doing is particularly difficult. Alongside our standardized X values. So we get our X values, we turn them into Z-scores. We can then take those Z-scores and, using a particular table, which I think is often referred to as like a Z-chart or a Z-table, we can convert those into probabilities. In particular, the table is going to take a z-score and tell you the amount of area to the left of that score. So this is going to describe the area to the left of a particular z-score. What does the area under our curve correspond to, though? Well, all of it is 1. And why is all of it 1? Because it's a PDF, because it's probability. And so another way to look at this is, yes, it's telling us something about the area, but maybe a better interpretation is it's telling us the probability that our value is less than or equal to a particular z-score. It's also telling us the likelihood that we see a z-score that is less than or greater than or whatever. In this case, less than this particular value, always to the left for what the table is giving us. Now, we can, so the table is just going to spit out the value that tells us to the left. We could take that value and manipulate it. And sometimes, or if we were doing this with tables, we would have to. So can compute to the right. Or like between two values. But the table just isn't going to give us that. Not to say that it's particularly hard. So for instance, if I wanted to know if I knew that this area, maybe my table tells me that this is like 30% of my data, then how much of my data does this area to the right of my z-score account for? How'd you guys do that? 100 minus 30? Yeah. So this would be 1 minus that 0.3 to tell you the leftover data. And that works perfectly. Like that, the way we convert from looking to the left versus looking to the right, 1 minus that probability and you're done. And that's easy. Yep. Okay, let's take a look at an example, and then we're going to break down what this is going to look like in the calculator as well. Okay, so looking at our example here, we are asked to find the area under the curve that lies to the left of the z-score 1.56. So area to the left is what the table is set up to tell us already, so we don't need to do any kind of interpretation piece. If we want to think about what this is going to look like, we'll have some kind of normal curve. Can do better than that. Like this. We got our median here, or our mean and all, whatever. And we say we have a z-score of 1.56. We are looking for the area to the left of this particular value. Okay. So all we're going to do is we're going to look at our table. The column tells us the ones digit and the tenths place, and then the row tells us the hundredths place. So 1.5 fits here, 0.06 fits here. We are looking at this value they overlap. And so that area is equal to 0.9406. What would I do if I wanted to find this area? Yeah, 1, or if we wanted to do percentage, subtract from 100. If we wanted to do just the decimal, we could subtract 1. So the area to the left is this. Area to the right is just 1 minus this 0.9406, which works out to be 0.594. Or sorry, rather 0.5. Sorry, 0.0594. I was going to say my decimals feel off. Yeah, it's not 59%. It's 5.9%. 0.0594. Okay, so what does it mean that our area is equal to this? Well, there are a couple of ways that we can think about it. First and foremost, this tells us that 94.06% of our data lives to the left of z is equal to 1.56. So a lot of our data living to the left of that z value. But another way to think about it is if I pick just a random z value, or if I get a random z value, what is the likelihood that it lands to the left of this value? Well, if 94.06% of them do this, then there should be a 94.06% chance that a random z value that I get falls to the left of this value. So in other words, the probability of getting a z-score that is less than or equal to, ultimately here it doesn't matter, 1.56 is equal to 0.9406. And both of these are valid interpretations of this. Actually, they're both important and different interpretations of what we are seeing here. Okay, a couple of pieces here that I want to dissect. What is the largest z-score that this describes? In other words, what is the upper bound that we are seeing to if we are looking to the left of 1.56? Yeah, what's the largest? Yeah, what's the largest z-score that this describes? For this? Don't overthink it. This isn't a trick question. What's the largest z-score that falls to the left of this value? No, that's the area under the curve. I'm looking at the z-score. What is the x value that's the largest that we can see? 1.56. So 5.5 is a good guess. But we want to get as close as possible. We could get like 5.9999999. We're going to assume that you get into some real analysis here, which we're not going to delve into. We count this upper bound as being the largest thing. So this 1.56 rather is essentially the point that we're not going to get larger. We're not going to see any z-scores that are bigger than this. Okay. What would our lower bound be? Is there a limit to what our z-score is allowed to be in the negative direction? No, it's never going to touch the x-axis. You could consider this negative infinity. We're not actually going to be able to plug negative infinity into our calculator. We're just going to call it like negative 100. This is not true But by the time we go out 100 standard deviations, we've basically covered all of our data. It's not true, but it's good enough. Okay, so let's take a look here at how we would do this. We are going, and we're going to get an ad, and I'm very excited for education with ads. We are going to not the normal PDF, but we're going to go to the normal CDF. PDFs tell us the probability at a particular value. CDFs tell us area under the curve. So that'll tell us the area that we are looking for here. We're going to the normal CDF. In this case, we said our lower bound technically was negative infinity, but we can't actually put in negative infinity. Negative 100 is good enough. You could try negative 1,000. You could do negative 1,000,000,000. You're going to get the same answer because we've covered so much of our data by the time we get to negative 100 that it's good enough. If you go second and then the vars button, which is around the arrow keys. All right, and we're going to set our lower bound, just some largish negative number. Honestly, anything more negative than -5 is probably good enough. But I just do negative 100 is just like, you're not going to see change after that. Okay, what is our upper bound, did we say? We said 1.56 was the largest we could get. If we're using a standardized score, what is our standardized mean? It's the one that's already in your calculator. What's our standardized mean? 0. And what's the standardized standard deviation? 1. So we'll let mu be 0. And we'll let the standard deviation be 1. And we get exactly the thing that our table gave us. Yeah, normal CDF. What's our lower bound? No. What's our lower bound? Nope. Nope.
Lower bound is negative 100.
It's technically negative infinity, but we're just going to put in negative 100 because that's good enough. Technically, -5 is also probably good enough. You'll notice here, if I change this to -5, which I'll do just for demonstrative purposes, you'll see that it does, in fact, change. But like, look how much it changed by. Like, hardly any at all, right? -5 is pretty close to good enough. -100 ensures that we're really, really happy. If I were to go in and try like -10,000 instead, like let's add some zeros, then we're going to see at that point, we're not adding any more data. We're not adding any more probability. It's not picking anything up. So -100, good enough. -10 is probably also good enough. Try it, right? And see if it gives us something different. -10, also perfectly good enough. Right. Okay, what if we wanted to do the area to the right? So if I'm looking at this area to the right, what would my upper bound be? Is there a limit if I'm looking to the right of my value, if I'm looking this way? Is there a limit on what I would expect to see? No. So infinity, but what are we going to put into our calculators? Sure, we can do 100. 10 also probably would work, but we'll just enter 100 because that's good enough. And then what would our lower bound be? What's the lowest possible z-score we want to include? 1.56. So the upper bound is now infinity, lower bound, the lowest value that we want to see is this 1.56. And we can plug that into our distribution here. Right, we said that that's 100. That this is 1.56. And we get the exact thing that we predicted, which was 0.0594. Which is the same as 1 minus the area to the left, right? Exactly the same. And either way we go about doing this is totally fine. Should we try another example? Sure.
Yeah, the normal always what's the lower and upper, right?
No, it's if we're looking to the left versus if we're looking to the right.
Okay, so second words, normal seems-
So take a stab. Let's take a stab at this example here.
Okay.
I want you guys to find both the area to the right and also the area to the left of the z-score 0.50. So we'll take like, I guess, a minute to knock that out. Okay, so what did we enter here to figure out the area to the left? What was our upper bound and our lower bound?
Area to the right, 0.
So do we want to do to the right first?
Yeah, sure.
Sure, let's do to the right first. We'll clear this. So to the right, what was our upper bound?
0.8.
Yep. So 0.50. And then what is our, so lower bound 0.50, what's our upper bound? 100 or 1,000 or 10, anything big enough. Standard mean, standard deviation. I get that makes up for about 0.3085. So that's our area to the right, was 0.3085. Or in other words, the probability that our z-score is greater than 0.5, right? To the right of means greater than, should be about a 30.85% chance. What could I then do to find the area to the left? So we could either do 1 minus, or we could make the 0.5 the upper bound. And either way would work. So if we wanted to make this the upper bound, we could use -10 or -100 or what have you. It doesn't matter. 0.050. I get 0.6915 as the other area.
Oh, I did the wrong one. I did the top one.
What'd you get for the top one?
Right was like 7.
79, like 6, 7. So 797. And then area to the left was
0.8.
203. Perfect. Yep, perfect. Very nice. Sure. And of course, if we did this, 1 minus our area to the left, then we get the exact same thing, right? Or rather, 1 minus the area to the right to get the area to the left. Of course, exactly. So, table's cool and all. You guys aren't getting a table on the SDC test. So, this is what we are pigeonholed into doing. Who cares that AP gets this table? Or that this is just how statistics is often done.
So AP, AP gets the table.
Yep, but we do not. So we just use our calculators. Okay, one more problem type for 5.4, which, if we were using the table, would be a little bit tricky. Since we're not using the table, it's actually not tricky at all. But I want to look at it, the conceptual way of how we would do this, and then we'll just discuss why this is just completely trivialized by the way that we are doing this. And that is finding the area between two different z-scores. Okay. So we have our normal distribution. We've got our first z-score at negative 1.23, second z-score at positive 0.96. If I look at the area to the left of my leftmost z-score here, what area is that going to fill in for me? What would the table tell me? What's the table going to tell me here?
It's going to be.
Well, it's just going to be this little triangle right here, right? Whatever this is. And we can look at the table, or you can plug it into your calculator. Either way should be fine. If I do the exact same thing for 0.96, what area is that going to look like? Well, if I'm still looking to the left, it'll be this whole area right here. And so if I just want to find the area between these two z-scores, what do I have to do? Yeah, subtract everything to the left of, I think, negative 1.23. We're counting one little area bit twice. We actually don't want to count it at all. And so we need to subtract the two in order to make it go away. Okay, so what we could do here, and this would totally work, we could take the area to the left of our first z-score. So the area to the left of 0.96, and we could subtract away the area to the left of our leftmost z-score, which is negative 1.23. And what we get is that this area is 0.7221. So this would be if we were doing this with the tables, right? The tables just give us the values to the left, but our calculators are better than that. So what am I going to do in my calculator to produce the exact same result? What's my lower bound going to be? So what's the lowest possible z-score I could see for the area that we are looking at here? Negative 1.23. And what's the largest possible z-score that we could see? 0.96. And so if I want to figure out the area between them, that's my lower bound, that's my upper bound. Sure, so the lower bound is going to be negative 1.23. The upper bound is going to be 0.96. It is the exact same thing. So like the only semblance of difficulty trivialized entirely by the calculator. And you just have to make sure that your lower bound is in fact lower and your upper bound is in fact larger, right? As long as you don't mess that up, this is fairly trivial. All right, questions with 5.4? That's it. That's 5.4.
Yeah.
Yeah.
So, let's. Can you go over the problem one more time?
So what's our lower bound? What's the lowest possible z-score? Is that the lowest possible z-score? If we're looking for z-scores between negative 1.23 and 0.96? No, what's the lowest possible? Negative 1.23. What's the highest z-score? What's the upper bound? So in your calculator, lower bound is the lower bound, upper bound is the upper bound. Yep, that's it.
So on the quiz tomorrow,
This is not on the quiz tomorrow. Yeah. This is not on the quiz tomorrow. Quiz is over 5.1 through 5.3. So probability distribution functions, mean, variance, standard deviation, and then the binomial. Okay, I do want to briefly at least show you guys 5.5. 5.5 is very, very fast. We'll go over some of the quote unquote trickier problems from it tomorrow. The main limiter is that my calculator that I have doesn't work as well as the calculators that you guys have. And so you guys are able to do things. I have to jump through hoops on this to do the thing that you are able to do with just a click of a button, which is, I mean, nice for you all, but then makes the demonstrative a little bit difficult. So our normal CDF is taking in z-scores and spitting out areas. 5.5 does the opposite. It gives us an area and it asks for a z-score. Normally what this would mean is like scouring the table for a particular value. So for instance, looking at this first example here, trying to find the z-score that would give us an area to the left of our curve of 0.0188. To the left of our curve is actually the areas that the table is telling us. So we would just look through that table for 0.0188, which we would find. Yep, exactly. This is negative 2.08. And that would be it if we were given the table. We are not given the table. And so we need to, I mean, it's not going to take much, but we are going to need to do something. Now, if I had given you the area to the right, so if I gave you area to the right, notice that the table only gives us areas to the left. So you would need to do 1 minus the area to the right to get the area to the left. Certainly could do that. That would not be particularly trying. And then we could scour the table and that would be fine. But our calculator is just going to do this for us. My calculator only gives me area to the left. So it basically is like the table. You guys can set your calculator to be area to the left or area to the right, or even area between two z-scores, which is pretty cool. Mine doesn't do that though. So if I go to second distribution, what we are going to want to do here, our normal CDF took in z-scores and spat out areas. our inverse normal is going to take in z-scores, or rather take in areas completely backwards here. Normal CDF took in z-scores. Whatever. This is going to do what we want. It's going to take an area. It's going to spit out z-score. Inverse normal. Yeah. So inverse normal. Yeah, you get to pick. Do you want left? Do you want right? Do you want it in between two values? Mine doesn't do that. Second dist. Second vars. Second vars. Inverse normal.
And it doesn't matter, like the z-score you put in there.
Well, so what you're putting in is the area that's being specified. So in this case, we're being told that the area under the curve that we are looking for is 0.0188. So the area, 0.0188. We still have standard mean, standard deviation. And so the z-score that corresponds to this area, you're going to be selecting to the left because you're being asked to do to the left. Mine defaults to the left. And what you get is a z-score of exactly what we found from the table, negative 2.08.
I got negative 2.8.
So like not particularly, not like harder than doing the table, but also, I don't know, it's not like easier. You can just look at the table and circle the thing.
Because the z-scores are like in the tens place, negative 2, and they're like in the hundredths place.
Yeah, so we round to 2 decimals for our z-score. Yeah, always.
It says the area to the right is the same number.
Is it positive or
It's
negative?
positive.
It's giving you positive? Yeah, so Merrick here has made a cool observation here, which is he did the same area to the right, and rather than getting the negative version of the z-score, he got the positive version of the z-score. That is not an accident, actually. That is a consequence of the fact that our distribution is symmetric. So for instance, having a z-score of 1 versus having a z-score of -1 puts you the same distance in the distribution, just on opposite sides. So for instance, if we were looking at a z-score of 1 versus a z-score of -1, we would expect the area to the left of -1 to match the area to the right of +1. Those areas should be the same, which is why you're seeing what you're seeing. Thank you. Yeah, so just be careful about the direction that you're focusing on. But yes, it is going to give you something comparable. Okay, let's take a look at one that is to the right. So for my calculator, it can only do to the left. So you guys try this to the right here. In this case, we're being told that the area is to the right of z, 0.0239. I'm going to need to convert that to an area to the left and then do the same thing. So how do I convert this to, how do I take area to the right and convert it to area to the left? 1 minus, you guys don't even have to do this, but I do. So 0.0239. That's going to get me 1 minus 0.0239. I get 0.9761 for my area to the left, and then I'm just going to do my inverse normal with this 9761, and what you guys should get is a z-score of 1.98. If you had just done this to the right. You could do the 1 minus and then do it to the left as well, and that's fine. But I get a z-score of 1.98.
So whatever it says right here.
This is not my recommendation for what to do. I have to figure out a workaround because mine only does to the left. My recommendation is to just switch your calculator's version to do to the right and then just enter in the area as you see it. But I do have this workaround, so this is what I have. Okay, so we have to the left, we have to the right. And then center is going to tell us the two z-scores that are like equidistant from the mean that capture that amount of area. I don't actually have a particularly, I'm sure I could finagle one. I don't have a particularly clever way to go about doing this to my knowledge. So I'm just going to have to trust you guys with whatever you get. So let's take a look at, we want to find the two z-scores such that the area between them is equal to 0.74. So again, we're going vars, we're going inverse normal. In this case, we want 0.74 to be the area. We want the tail to be set to center. And the z-scores that I get are between z is equal to negative 1.126 and positive 1.126, which captures that 74%. It's actually not too bad to figure out for the other one. It's not horrible, but I don't want to do it, so I'm not going to. Actually, that's a lie. It's actually a fun little math problem, but we don't need to do it, so we will not.
Oh, but you can just look at the so like you find that number on here.
All right, questions with the area functions on our calculator? 5.4 or 5.5? Any questions? Feeling okay? Easy peasy. Bit mind numbing.
This is the z-score. 0.0. I don't know. I think I don't know. It's supposed to equal 1.
Okay, there is technically one more thing to cover in 5.5. I'm pretty sure it is just converting between x values and z-scores, which we've already done. We'll do a little bit of practice with that later on in this week, so we'll do a little bit of practice with that tomorrow and the day after. So we've got about 10 minutes left. You guys have the rest of this time to work on classworks, get ready for the quiz that we have tomorrow. If you have any questions, of course, feel free to ask. I'd be more than happy to take a look at things. And beyond that, go to have fun. Yes.
How long does the seminar during the half day?
I don't think we'll have seminar. But I don't know. Don't quote me on that though, because I don't know. They probably did send out the schedule. I did. There's one of these. Okay, one of these is today's and one of these is yesterday's. Because I didn't get one yesterday. This is the bus.
Are you like, but I don't see you on like the bus, you know, like near the bus.
No, I point people towards what buses to go to.
Can you tell me your bus to do?
I don't know which of these is today's and which of them is yesterday's. I can give you a 50% chance where it is. What bus number?
30816.
Well, they're relatively similar, so it's not too horrible.
Okay.
You're either third from the front or fifth from the front. So far side.
Oh, there. All right.
Yes,
Turning this in, but I don't remember what I was supposed to round everything to. Not gonna lie.
3 decimals.
Ooh, I did too.